So we just talked about how the polarization of an alkyl halide makes it reactive, and we saw that right here with the electrostatic potential maps, and essentially the carbon next to the halogen has a big partial positive charge on it. So how are these alkyl halides going to react then? And what I have written up here, and it's in your notes as well, is that alkyl halides undergo nucleophilic substitution reactions, and that there's two types of those reactions. The first type that we're going to talk about in depth is called an SN2 reaction, and all of those things have some meaning to it, the S, the N, and the 2. So S stands for substitution. The N stands for nucleophilic. So when we're talking about organic chemistry, we're always talking about what is happening to the carbons, right? And on these carbons, we're substituting a nucleophile onto that carbon. So that's why it's substitution, nucleophilic. And we talked about how this is the electrophile. There's a big partial positive right there because of the partial negative of the chlorine, which makes that a very electrophilic carbon. And then 2, what does the 2 stand for? The 2 stands for bimolecular. So essentially, how many reactants are involved in the rate determining step? So yeah, how many reactants are involved in the rate determining step? In an SN2 reaction, 2 reactants are involved in that rate determining step. So the 2 stands for bimolecular. So the 2 stands for bimolecular. So that would mean that this reactant and this reactant are involved in the rate determining step. So how does this transition to this stuff? That's something that you guys should be ready to do mechanistically. How did these 2 species become these 2 species? Remember, we push arrows. The arrow head is where the electrons are going. The arrow tail is where they are coming from. So pause the video for a second and try to draw a mechanism showing how these 2 things become those 2 things, because that's something that we should be ready to do now, even without me, since we know that it's happening in a single step. This is a concerted reaction. So we'll say that this is a concerted one-step reaction. This is an SN2 reaction. So again, go ahead and pause the video and do that. All right, you did it. You did a great job. This is what you drew in there. So the oxygen is making a new connection to the carbon right there. So we draw the electrons from the oxygen coming and adding to there. We can't just add that, because if we just added that, then this carbon would be over its octet, right? It already has 1, 2, and then has 2 hydrogens on there. Already had 4 bonds. So a bond has to break. The way that the bond breaks is that the chlorine takes its electrons to itself. And we can see that because the chlorine has 4 lone pairs there. Oxygen only has 2 lone pairs here. It had 3 lone pairs here. So it used one of those lone pairs in that reaction. So SN2 reactions, the carbon piece is always the electrophile. We call this the E+. And this was the nucleophile. It supplied the electrons. It loves nuclei. It loves positive charges. So this was our nucleophile. So this is nucleophilic substitution. We broke the carbon-chlorine bond and we made the carbon-oxygen bond. So what would a reaction coordinate diagram look like? So let's do a reaction coordinate diagram. And I'm going to tell you that this reaction is exothermic. It is an exothermic reaction. So take a minute to pause the video again and draw yourself a reaction coordinate diagram. What would you expect this to look like? Okay, so you've done that. You've paused it. You're back with me. It's exothermic, so we know that the products are lower in energy than the starting materials. How many hills are we going to have? Well, we need a hill for every step in a reaction mechanism. This happens in a single step. That happens at the same time that happens. So the starting material only goes through one transition state to the products. Just one hill here because this is a totally concerted reaction. What would the rate be equal to here? So the rate of this SN2 reaction equals the rate constant. And then what's here? That's another chapter 6 concept. You guys should know what would be over there. So pause it, add your own, then come back. You've done that. Well, the rate is equal to the rate constant K multiplied by the concentration of the reactants that are involved in the rate determining step. There's only one step here, so that must be the rate determining step. So it's equal to the concentration of the alkyl halide multiplied by the concentration of the hydroxide ion. Okay, so what else do we know how to do already? We also know how to draw the transition state. So again, pause the video for a second. Take a minute, draw the transition state. All right, you did a great job of that. So what did we do? We look at what bonds are formed and broken. The bond that was formed is an OC bond, so that's going to be a partial bond. The bond that was broken is a CCl bond, so that's going to be a partial bond. So in the transition state, we have a partial bond between the nucleophile and the carbon, and a partial bond between the leaving group, the chlorine, and that carbon. What am I forgetting here? What did you all already have on there? The charges, right? Yeah, the charges. So the charges that we put in charges onto anything that was a charge and is no longer a charge. So oxygen had a negative charge on it. In the product, it is neutral. So it's going to have a partial minus charge on it right there. What else? The chlorine is neutral over here. At least formally, we know that it has a partial negative on it, but the formal charge of that chlorine in the structure is neutral. In the product, it's minus, so this is a partial minus. So that would be the transition state. So these are kind of all the nuts and bolts of an SN2 reaction. You can see that kind of once I told you that it's concerted, once I told you that both of them are involved, you could kind of already figure out all of this stuff. And even the mechanism itself, just knowing that it's a concerted reaction, all the bonds had to be formed and broken simultaneously. So again, let's drive home that same terminology, and we're going to get more into the specifics of the SN2 reaction, especially regarding the rate in the future. So look forward to that.